All right, let's just jump right into it. Welcome to this explainer. Today, we're taking a look at the invisible forces that literally power our everyday lives. Seriously, if you flipped a light switch, cooked on a modern stove, or even just set your phone on a wireless charger this morning, you are actively using the exact physics we're going to break down today.
But before we get into the math and the diagrams, think about how wild this is. How do modern marvels actually work without any physical connections? It's kind of the ultimate question of invisible magic, right? Like, how does dropping a simple magnet relate to the massive electrical grid powering your entire city? We are totally surrounded by these unseen forces, and unpacking them is basically the key to all modern engineering.
So here is our roadmap for unpacking this mystery. We're hitting 1. The magic of invisible forces. 2. Faraday's groundbreaking experiments. 3. The laws of induction. 4. Lenz's law, which is nature's pushback. 5. The math behind the magic. And finally, 6. Powering our modern world. Starting off with Section 1, the magic of invisible forces. Let's talk about the magnetic fields all around us. Okay, so the absolute bedrock concept here is electromagnetic induction. Basically, this is the process where a changing magnetic field induces an electric current to flow. If you move a wire through a magnetic field, or just change the field strength around a wire that is sitting perfectly still, a current is going to flow completely on its own. No batteries required. It's this incredibly direct conversion of physical movement into pure electrical energy. Moving to Section 2, Faraday's groundbreaking experiments. To see how we harness this today, we've got to travel back and look at how it was actually discovered.
The 19th century was just an unbelievable time for physics. Michael Faraday kicked it all off in 1831 when he proposed electromagnetic induction. Then, incredibly closely after, in 1834, German physicist Emil Lenz jumped in to detail the specific direction of that induced current. And by 1845, Franz Ernst Neumann wrapped it all up by establishing the strict mathematical form that unified the whole thing. Such a golden era of discovery.
So how did Faraday figure this out? He didn't just guess, right? He used empirical data from 3 really simple, distinct experiments using just magnets, wire loops, and an ammeter to measure the current. First up, he moved a magnet toward a wire loop and bam, the ammeter jumped. Second, he rotated a magnet near a coil, which proved that relative motion was the key. When the magnet just sat there stationary, absolutely nothing happened. And third, he pulled the magnet away from the loop and the ammeter deflected in the exact opposite direction. From there, he defined the core physics. Section 3, the laws of induction. First, we've got to define the result. When Faraday moved that magnet, he induced what we call an electromotive force, or EMF. Now, quick side note, even though it has the word force right there in the name, EMF isn't actually a mechanical force. It's really the potential difference, the voltage that actively drives the electric current through the wire. Think of it as the energetic push. The other huge ingredient is magnetic flux. A great way to visualize magnetic flux is to picture water flowing through a hula hoop. The water represents your magnetic field lines, and the hoop is your loop of wire. More water flowing or a bigger hoop, you get greater flux. If you tilt the hoop, less water gets through. It's the exact same deal with magnetic fields passing through a conductive area. Which perfectly sets up Faraday's first law. This establishes the when. It tells us that an electromotive force is induced whenever the magnetic flux across a coil changes with time. So if the field changes strength, or if there's relative motion between your magnet and coil, an EMF is born. If nothing changes, no EMF. It's entirely dependent on dynamic movement or fluctuation. Then we get the how much in Faraday's second law. It states the induced EMF in a coil is equal to the rate of change of flux linkage. Put simply, the faster you change that flux, like the faster you yank that magnet or shift the field, the more voltage you get. Speed and intensity of change directly translate to more power. But nature doesn't just hand out free energy without a fight. Section 4, Lenz's law, nature's pushback. Heinrich Friedrich Lenz stepped in to figure out the direction of this energy, stating, "The polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it." This all comes down to the conservation of energy. You literally cannot create energy out of nowhere without some physical consequence. I always like to think of Lenz's law as nature's rebellious teenager. It stubbornly hates change and it's always going to push back. Whenever you alter the magnetic system, say by shoving a magnet in, the newly induced current creates its own magnetic field specifically to oppose you. Push the magnet in, the coil's field pushes it out. Pull it away, the coil tries to pull it right back.
To clearly contrast the two, Faraday's law gives us the magnitude, the sheer amount of voltage we're playing with. Lenz's law gives us the direction of that current, the opposition. Faraday is the raw power, and Lenz provides the direction, which adds a very crucial negative sign to our final math equation.
Speaking of math, let's hit section 5, the math behind the magic.
Here is how it all beautifully comes together for engineers. The equation is epsilon equals negative n times the change in phi over the change in time. Epsilon is the induced EMF, our voltage. See that negative sign right at the front? That's Lenz's law, nature's pushback in mathematical form. N is the number of turns in the coil because wrapping the wire 10 times multiplies the effect by 10. And finally, the change in phi over the change in time is the rate of change of our magnetic flux, tying right back to our water flow analogy.
And if you thought this was just about basic motors, get this. Albert Einstein actually noted that much of the groundwork for his special relativity theory was presented by Faraday's law of induction. The way relative motion worked between a magnet and a conductor, regardless of which one was actually doing the moving, fundamentally shaped how Einstein viewed the entire universe and the relativity of space and time.
Kind of mind-blowing, right?
Let's bring all this heavy physics home. Section 6, powering our modern world.
From the wireless charging pad on your nightstand to the wailing solo of an electric guitar, this one principle of induction is absolutely everywhere. It's why transformers can safely step down high AC voltage before it hits your house. It's how modern induction cooktops heat up your dinner using rapidly changing magnetic fields instead of an open flame. It's even doing the heavy lifting in MRI machines and electromagnetic flow meters.
The true, profound impact here is scale. The exact same math that measures a little magnet falling through a copper tube is currently powering the electrical grid of your entire city. Massive electric generators at power plants are, essentially, just gigantic versions of Faraday's wire loops, spinning at crazy speeds inside massive magnetic fields to push EMF out to millions of homes. One elegant rule of physics literally lights up our modern world.
It definitely makes you stop and wonder, if a simple piece of wire and a magnet from 1831 can power our entire lives today, what invisible force might we discover tomorrow?